Hello, my name is Lisa Pivnik, and this is my Physics 2 Lab 4, where we looked at circuits and capacitors. So an introduction to this lab, in this lab we used an online circuit construction kit to explore time-dependent voltage and current in a DC current circuit. And then the concepts of loop rule and node rule in circuits was utilized here. And then resistors and capacitors were also used, and the behavior of the current and voltage were observed while using them. And additionally, the differences between resistors in series and parallel were explored. So here are the main physics concepts. We have Ohm's law, where voltage is current times resistance, and then the capacitance is charge divided by voltage, and then our node and loop rule, where current in equals current out, and the total potential difference around the entire circuit is equal to 0. And you can see the loop rule demonstrated in the picture below. So for the circuit simulation, for the first part of it, we built a circuit with two 1.5 volt batteries, two ammeters, and 47 ohm resistor and a 100 ohm resistor in series. And then the predicted current around would be V divided by R, so around 0.0204 amps. And then the actual current measured in the simulation was 0.02, which is exactly what's expected. And then when you reverse the ammeter, it was negative 0.02 amps, which makes sense. It's the same magnitude, but opposite signs. And then when we added a voltmeter to it, it became an open circuit, so the current was no longer flowing through the circuit. So you would expect a 3 volt potential at the battery and a 0 volt potential at the ammeter. And this is exactly what happened when we did it in the online simulation. And then once you close the circuit, now you have a current running through the whole circuit. So we replaced the voltmeter with a wire, and thus closed the circuit. So we measured the potential differences across various points on the circuit, and then we made a graph of the changes in the potential difference at each of these points. So here was the result of this, and here you can see my graph on the right. We can see that the delta V round trip was 0, which exactly supports the loop rule. So you can see it was positive across the battery and then negative across the resistors. And then we also tried putting the ammeter in parallel, and this increased the current from 0.02 amps to 0.06 amps. And this is because due to the parallel ammeter, less current encounters the 100 ohm resistor. It goes through the alternate path and only goes through the 47 ohm resistor. And thus, since our resistance went down, our current went up since our V did not change. And the current is the same everywhere. So both ammeters read 0.06 amps. And then we also calculated resistance in several spots. Our calculated resistance was 48 for the 47 ohm resistor and 102 for the 100 ohm resistor. And then as expected, it was 0 for the wire and ammeter. So these calculations were pretty close to the realistic numbers. And they also support the assumption that there's no resistance in the ammeters or the wires. And of course, they're not completely accurate due to the lack of precision in the measurements of potential difference and current. So the second part of the lab, we built an RC circuit, so a circuit with a capacitor and a resistor. And there was a 100 ohm bulb, a 20 ohm bulb, one 9 volt battery, and then a 200 farad capacitor. So when the capacitor was charging, the maximum current was reached at first, and the bulb was the brightest, but then the light and current both decreased exponentially with time. And then when the capacitor was fully charged, there was no current and the bulb was not lit. And then the charging times that I measured were about 10.1 seconds for the 10 ohm bulb and 19.8 seconds for the 20 ohm bulb. And then when the capacitor was discharging, we had a very similar decrease happen. So the maximum current at first was achieved in the beginning and the bulb was the brightest. And then again, the decreased exponentially and it was fully discharged. There was no current. So the current also flowed in the opposite direction when it was discharging. And the discharge times was 13.4 seconds for the 10 ohm bulb and 27.5 seconds for the 20 ohm bulb. And these make sense because both the charging and discharging times were about twice as long for the 20 ohm bulb since it had more of a resistance. So then we could also calculate our RC, or the time constant of the circuit, which is the time at which the voltage has dropped to 1 over E of its original value. And we just used the original voltage and loop equation and we rearranged it and did an integral, and this was the result. And so what we could do is graph the natural log of your voltage over your initial voltage and versus your time, and then the slope would be -1 over the RC. So this is exactly what we did in this lab. So you can see in my Excel plot, the slope of this line was -0.1456. And if you take the negative inverse of that, you get 6.87 seconds as your experimental RC value, and the theoretical value was around 6. So we came pretty close to this value from our data over 20 seconds. And some additional questions for this lab. What if you were doing this lab in real life and using an actual ammeter instead of an ideal simulated one? What's the difference? And the difference would be that it has some resistance, meaning the currents going through it would be smaller than they were with the online simulation. And then real life readings would be less true for the light bulbs, resistors in the circuit. And then additionally, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And then would this happen in real life? So ideally, the capacitor would be charged instantaneously if there was no resistance, but realistically, there is resistance in the wires and other components of the circuit, and so therefore, it would take some time for the capacitor to charge. So this concludes my Physics 2 Lab 4, and thank you for listening.